Hello everyone. I'm Sai Venkatakrishan, a PhD scholar in the Department of Computer Science and Engineering in IIT Madras. This is week 11 live session for the NPTEL course Operating Systems Fundamentals. The agenda of this session would be we'll be discussing few questions pertaining to the week 11 syllabus, that is virtual memory management. And the main aim of these live sessions is to clarify your doubts in these topics and to facilitate you to better approach the current assignment questions that are released on the NPTEL portal. So you can post your questions in the chat box or you can unmute yourself and speak. So let's get started then. So this is the first question. Provided that the memory access time is given as 300 nanoseconds and your average page fault rate is service time is 12 milliseconds and the page fault rate is 0.0001. Find out the factor by which the access time is slowed down. So they have given your page fault time, which is 12 milliseconds, and then so this will happen if there is a page fault. So to get the page from the disk into the memory and all those things. And they have also given your memory access time, which is 300 nanoseconds, and the page fault rate is 0.0001. So given these three information, they are asking us to find what's the slowdown. So any guesses what the slowdown might be, or how do you go about calculating the slowdown? Right. So the approach is very simple. First, we should calculate what's the memory, the effective memory access time. So that's nothing but so this is the page fault rate. We take this as P. So 1 minus P. So this is like the hit ratio. So this much percentage of times it's always present in the memory, whatever page you are requesting. So this is the hit ratio 1 minus b into 300 nanoseconds, which is the time taken to retrieve a page from the memory which present, which is 300 nanoseconds, plus the remaining p times is the time when the page fault occurs and it's not present in memory. So when it's not present in memory, it will be around they have given 12 milliseconds. So this is like 12 milliseconds is 12 into 10 power 6 nanoseconds. So just substituting 0.0001 in this answer in this p, right? 1 minus p and these things. The final answer you will be getting is 1500 nanoseconds. You can just substitute and see for yourself. Okay. So substituting p, you will get 1500 nanoseconds. So this is your effective memory access time under these set of conditions. When your page fault rate is this, and the service time when a page fault occurs, it's 12 milliseconds. Under these conditions, the effective memory access time is 1500 nanoseconds. But they have specifically asked what's the slowdown. So by slowdown, how do we calculate this? In an ideal scenario, what's the memory access time? So the ideal scenario is all pages you are requesting should be present in your memory always. So in the case like your page fault rate is should be 0. So if your page fault rate is 0, substituting in this formula, right? The in this formula, so substituting for page p equal to 0, it should be 300 nanoseconds. Your ideal memory access time. Sorry, 300 nanoseconds. So which is the ideal condition. All your pages are present in memory. There is no page fault. So no page fault service routines. Nothing comes in between. You have to just access that virtual address or the physical address and get your data. So this is your ideal time. So now the slowdown is nothing but how many times it has slowed down is 1005 by 300. So it is like 5 times it has slowed down. Compared to the ideal scenario, when the page fault rate is 0.001 and your page fault service routine takes 12 milliseconds, then the slowdown is 5 times. It increases by 5 your effective memory access time compared to your ideal memory access time. So the correct answer is option B, 5.
I have a question.
Right.
Do you take classes in IIT Madras? I mean, as a teaching assistant.
Uh, can you ask the question in the ending?
Okay, sure.
Yeah, okay. No, because this is like recorded, right? So I will answer that in the end once these things are over.
Okay, sure, no problem.
So is there any doubts in this question?
No.
Cool. So in that case, let's move to question 2. In a system with 32-bit virtual address and 1 KB page size, if you are using one level page tables for the virtual to physical address translation, this is not practical because of which reason? Does it result in large amount of internal fragmentation or external fragmentation, or is it due to the whole virtual to physical address translation is very costly, or the memory overhead in maintaining these page tables is very huge? Any guesses which the option is correct? Okay, Nandan mentions option D. Any other guess or any other answer? Right.
I'm sorry, actually, I didn't get through the lectures yet, so I can't.
Okay, no worries. So, so as Nandan has mentioned, option D is the correct answer. The reason being, if you take a 32-bit virtual address space, right? So 32-bit virtual address. So you have to, and the page size is 1 KB. So it's basically like 2 power 32. So each so assume it's byte addressable system. So each address, each change in the bit corresponds to a different byte. So 2 power 32 bytes are present. So the total number of virtual pages would be 2 power 32 divided by 2 power, is it 12? I guess so. 2 power 12 is, I guess so. 2 power 12 is
So
101 KB.
about 1 kV 2 by 10 bit, I think.
Okay, sorry. 2 power 10, okay. So 2 power 10, okay. So that's 1 KB, right? So in that case, these many virtual pages you would require. So these many virtual pages, if you require, then those many entries you should be requiring in your page tables to uniquely map these many virtual pages into a physical page. And since you are just using a one level page table, right, you should at once in the starting itself you should allocate these many number of virtual uh, page entries, these many number of entries you should be allocating into your one level page table. But the real world application would not be using all these pages at the same time. Some of these pages would not be used at all based on how your application flows. Say you just choose option 1 in your application and just uh, use that part of the program alone, then the remaining parts of the program, the other options associated with the other options, those should not be used at all. So in that case, those pages getting into memory and mapping it to a physical page from a virtual to physical page and maintaining those page table entries, it's a total waste. So that is why instead of using a one level page table, they go for like a two level or three level page table, such that the active memory space, if you are trying to maintain in the address translation in the page tables, it is more efficient to use a multi-level page table scheme instead of just going with a one level, a huge page table. Any doubts in this question?
No. Thank you.
Okay, cool. Then let's move to third question. So page replacement algorithm, what does it want to achieve? Does it so this page replacement algorithm in the context of the main memory? Say like your memory is full and you want to access a new page, so you have to evict some page and get that required page into your memory. So what's the aim of the page replacement algorithm? Does it want the first access to itself have the lowest page fault, or does it want the re-access to have the highest page fault, or none of the above? So what's the main aim of your page replacement algorithm in your main memory? What does it want to achieve?
Is it A?
Right. So the correct answer is option A. The main aim of page replacement algorithm is not only the first access, the re-access also it wants to have a lowest page fault. So the main aim is so that most uh, all your active pages, given your number of frames allocated to your process, right? It's like say your process P1 is using is allocated 10 frames. This is physical frames, and it is actively using 9 pages in its virtual memory, in its virtual address space. So these 9 pages should always be mapped into the 10 frames, so that it's always present in memory. So that's the main aim of your page replacement algorithm, so that your overall memory access time is efficient and it's less. So that's what your page replacement algorithm tries to aim for. Just if these frames are say you're just having 8 frames, and these are 9 pages you're actively using. So among these 9 pages, which are the most frequently used 7 pages or 8 pages, you should try to find out and keep them always in the main memory and swap out one page and do some sort of design and replacement algorithm. So the main aim is to have the first access as well as the other recurring accesses also to have the lowest page fault always. So that's the main aim of your page replacement algorithm. Any doubts in this question?
No.
Okay. So in that case, let's move to question 4. What is Bailady's anomaly? So when we use first in first out replacement, and when we increase the frame counts allocated to that process, it does not affect the page fault count. Is that Bailady's anomaly? Or when we use FIFO for page replacement and we increase the frames, it reduces the page fault count. Is it that, or is it option C? More frames leads to more page faults under the FIFO page replacement. So Nandan has mentioned option C, right? So option C is the correct answer. The reason being, what Bailady's anomaly is all about is the normal assumption is, say you have a process P1 and it has allocated 10 physical frames, okay, and if it is allocated more frames instead of 10, if it's allocated like say 15 physical frames, then the normal assumption is, okay, we are allocating more memory, so it will always perform well. Your page fault rate will decrease because you can bring in more set of pages, you can maintain it in your page tables. You can have more set of uh, the pages which you are using, that would be present in your physical frame, since there's an increase of 5 physical frames allocated to your process. So of course your memory performance will improve, because more the frames allocated, more the memory, more the pages are present in your memory. So you need not go through that page fault service routine and do and trigger off a page replacement algorithm or all those things. So that's the normal assumption. But in Validity anomaly, what happens is this assumption is proven wrong, especially in page replacement algorithms like FIFO. So in FIFO algorithm, when just blindly increasing the number of frames, it doesn't lead to, it doesn't reduce the page fault rate. Instead, it increases the page fault rate, which is not beneficial to us, to our case, because increasing the frames, we thought it would be reducing the page fault count, but it's doing the opposite. It's not just like remaining idle or just not like a constant level. Instead, it's increasing the page fault count. So that's what Validy's anomaly is all about. And this anomaly is present in FIFO page replacement algorithm, like first in, first out, and afterwards random page replacement algorithm, and a couple of others. So why this anomaly is present in these algorithms is because it it just it doesn't consider evicting like the evicting like a least used page or something like that. So some, it doesn't consider which pages are most actively used, or which pages are is recently used, or those things it doesn't consider. It just considers which one came first in its queue and takes that out. It might be the case that whatever came first would be say like your page, your access pattern is you're referring page 1 and you're referring page 2, you're referring page 1, you're referring page 3, and say only 2 frames are allocated. Okay, so and again it's page 1. So in first out, what happens is first your page 1 would be brought into memory. So page 1 is at position 1 and page 2 would be in position 2. So page 2 is the second page got in allocated to that frame, and now we are at this reference. So page 1, it's a hit. And now when it comes to page 3, it blindly, what it does based on FIFO, it will take out page 1 from the memory and allocate page 3. But the thing is that page 1 is being referenced twice, which is more than page 2. So it means that page 1 is more frequently used than page 2. So, but a FIFO or random algorithm doesn't consider these aspects into its replacement policy. So what happens is it blindly takes out page 1 and it gets page 3. And now when it wants page 1 again, it takes out page 2. So instead of taking page 1 right in the first place to get page 3, if it gets page, if it takes out page 2 and places page 3 in its position, this reference would be a hit because page 1 would be present in the memory. So this is what Validy's anomaly is. Also, if you, this is one case. If you increase the frame count, right? So in the lecture, the professor would have given a reference page reference count, and he would have and the number of frames would be increased and shown. And the thing is, even if the number of frames are increased, the page fault rate increases in FIFO policy, because it doesn't consider the recency or the frequency information of these pages, how they are used. So that's the main reason of why this anomaly occurs in FIFO or random replacement policies. So any doubts in this question? Right, Nandan, yes.
Like I still haven't convinced that like that why where the page fault is increase in the like
Right.
yeah.
Okay. So
Are there any mathematical reasoning sort of a proof to show that?
right. Proof. I'm not. There may be proofs in the research papers. I have not googled them actually, but the reason is this FIFO and random based. It doesn't consider these aspects, right? The recency information. That's the main intuitive reason behind Melody's anomaly. So,
Yeah, like
yeah, I get it. Like the intuitive thing is, if you increase your physical frames, you might you should get an improvement in your page fault rate. Uh,
or maybe it shouldn't affect it all, right? So like, why the increase in the page fault instead of like decreasing or staying at constant?
right. So let us try constructing one um, reference state and see what happens. One three. Uh, so initially assume like two frames are allocated. So this is frame 1, frame 2, and now this is um, so this will be 1 3 2. Okay, so give me a minute, okay? I'm if you
Yeah,
want, like
fine.
I can take the lecture note and copy that frame reference, but I guess you would have gone through that. Uh,
Or maybe we can like discuss at the end of this lecture, right?
yeah, sure. Or wait, I can just open that slide if you want. Which is frame allocation plus. Where does it come? Right. So they have taken this reference 1 2 3 4 1 2 5 1 2 3 4 5. Have you tried counting the number of page faults with 3 and 4 frames?
No, actually.
Okay, so can we just step through this reference string and see?
I think we just have to list the number of frames. It depends on number of frames. It's possible to list.
So if I just strike it like this, it means this resulted in a page fault, and if it's like this, it was a hit. Okay, we'll stick to this notation, and let's start then. So if it's at 1, so this one is so 1 is brought over here, and again 2 will be brought over here, and then 3. Okay, and now 4. So which one came first? So 4 will be brought over here, and now again 1. So this will be present over here, and now 2. So it will be 2. Okay. And now 5. So so 1, this will be a hit, this one, right? Are you following?
Yeah.
Okay, so this one will be a hit, and now again 2, this will be a hit. Now 3, which one came first? 1 came first, right? Like the last one was, we kept in 5. The first one, out of these 3 frames, the first one is 1, like 1 2 5. So this one is the first, so this one will be swapped out and it will be 3, okay, and now 4 and now 5, so 5 will be a hit. So totally out of only we are having just 3 hits and the remaining are all page faults. So the same thing, let's do it again. 1 2 3 4 1 2 5 1 2 3 4 5. So the same thing, let's do it for 4 frames now. Now if you see, so first it will be 1 2 3 4, all these things would be brought into memory, and now 1, it will be a hit, 2 will be a hit, okay, and 5 will be, sorry, 5 will be over here, 5 will be so 5 will be over here, and now 1, so it will be 1. Now 2 will come in place of 3, and 3 will come in place of 4. Now 4 will come in place of 5, and 5 will come in place of 1. So compared to this scenario where you had 3 frames and where you had 4 frames, you have 3 hits, whereas in this thing you had only 2 hits, right? Do you see that the page faults increased by 1? Nandan?
Yeah.
Yeah.
Okay.
So the reason is, if you consider where um, the where this difference, why it occurs is, um, if you increase the number of frames, um, say when at this position, like 1 2 is a hit, and now 5, so when you want to get in 5, you are evicting 1, and not so if you just consider these things, right, just consider this portion of your memory accesses. The number of times 1 and 2 are accessed, page 1 is accessed twice, page 2 twice, page 3 and page 4 is 1, right? So based on some other replacement policy, something which considers that number of times that page is accessed, so the more the number of times it is accessed, the more frequently it is being used, so it is most probably that a new page will also be accessed, that new reference that will be accessed will be pointing to this one of these p1 or p2 pages, the probability is higher. So that's what the LRU policy, those things are all focused on, that intuition, right? So if you consider LRU or something, it wouldn't have replaced P1 or P2 by and got in the fifth page in place of P1 or P2. Instead of, it would have chosen one of P3 or P4 actually, right? And also the other, but whereas in FIFO it just blindly considers whatever was accessed first, that should be thrown out. It's so that's what FIFO is about. And also the another reason which I came about is why this FIFO um, suffers from this anomaly when no, when compared to LRU, which doesn't suffer, right, these recency based or stack frame based allocations. The reason is, say um, if you increase the number of frames, say at this position, 2 3 4, uh, So say if you want, if you are just capturing that frame, the page to frame association at this point in the reference string. So after these many references, you are just capturing that, you are just pausing that reference string and seeing what your frame contents are, which page it's storing it. So if you see that in a FIFO, it will be like in the case of 3 frames, right? In the case of 3 frames, it will be 1, 2, 3, 4. So it will be 2, 3. Okay, it will be 4, and then 4, 2. So first it will be 1, 2, 3. Now this will be 4. This will be 1. This will be 2, and now 5 is also considered. So this will be 5. So at the end of this page reference, what my frame contents would be is frame 1 would be 5, next would be 1, and then 2. So this one is at position 1, this is at position 2, and this one was the last one. This is how they entered into your frames. Okay. Whereas in 4 frame count, if you notice how these FIFO ordering would be, let's see. So initially it would be like 1, 2, 3, 4. 1 would be a hit, 2 would be a hit, and now 5. Okay. Okay. So this is at 1, 2, 3, and 4. So 5 came in last. The remaining, this the order, the FIFO order. Okay. So any the intuition that uh, increasing your page frames, allocate the number of frames allocated to your process will decrease your page fault count is correct only when the when you are able to maintain that, increase your active working set present in your memory. So in the same way, this is for FIFO. We saw, if we had seen an LRU algorithm, the same, like if you just take F1 3 frames and 4 frames, F1, F2, F3, and F4. Okay. And now it is say 1, 2, 3, 4, 1, 2. Okay. So 1, 2, 3, and if 4 would be not, then you can, the 4, okay, 4 it could be, okay, something like, oh, does it degenerate into a FIFO least recently used? Okay, so if you just so this is what your LRU allocation would be at the end of this page allocation, after this page 5 is accessed, right? uh, like assuming that when all the pages are referenced only once, it degenerates into a FIFO mode. Let's just assume that, like when everything is accessed just only once, which one will be your victim frame, which one will be swapped out. Let's just assume FIFO mode is followed in that case alone. Okay, so in that case, after your all the access, right, it is 5 and 2, and if you increase your number of frames, okay, so it is 1, 2, 5 fold. So this is what your frame allocation would be. If you notice between FIFO and LRO, with just 3 frames, the see your active pages which are maintained in memory, it's the same set, page 5, page 1, and page 2 at the end of this reference point. But uh, if you increased your frame count to 4, and now if you see what your active pages are there in memory compared to the 3-page scenario. For LRU, it is the same 512 is present, and page 4 is also present in addition to these 3 pages, because you have a extra frame that is allocated to your process. But in a FIFO model, what happens is, if you see this, it is totally different. 512 is not present in this um, frame allocation when you have 4 frames. It is page 5, 2, 3 and 4. It's totally different. Okay, so this is because FIFO doesn't blindly increase your doesn't utilize the increase in page frames, and it doesn't meaningfully utilize that increase in number of frames. It just, okay, first in first out, it just follows whatever came first, just flow it out, and but it doesn't efficiently uh, take into consideration this recency information on all those things to utilize the extra frames that are being allocated to that process. So in an ideal scenario, whenever you are ideal scenario is nothing but whenever you are your increasing your number of frames, right? Your working set should be the uh, should be should be holding more. Your working set should be more, as in should increase. So what I mean by that is, say you are actively using 4 pages, page 4, page 1, page 2, and page 5. Okay, so if these are the 4 pages that you are using, and with just 3 frames allocated to you, you can just manage. You can just have any of these 3 pages only in your memory. But if you have 4 frames, you will be able to easily map all these 4 pages into the 4 frames. But the same you could not tell in FIFO model, because your working set, that is the most actively used pages, it is not guaranteed that it will be always maintained in your frames, because it the order in which they are evicted depends on the order in which they came in, and not based on how they are accessed. So FIFO is more about when they came in, it follows that approach, which is wrong, whereas the LRU policy is more about how much we have used that page, and how we had used it to find out that victim page. Anything you
But
understood?
I feel, I mean, if you see the structure, the people will be useful for, where number of frames are within, I mean, where we have only less number of pages accessible for the programming and for the process, right?
Sorry, I didn't get it.
I mean, if like the number of pages is very less, will FIFO will be useful in that scenario than LRU? I mean, is there any case where FIFO is better in terms of efficiency than LRU?
Right. So it depends on how your application works, right?
So
Uh,
yeah,
yeah.
I was thinking like when we need to use less number of pages, then I think FIFO will be completely better in terms of LRU. Is it?
Right. Um, Mostly, no.
Because like the concept of locality of reference is
Right.
more evident in LRU. If, if
Yeah. The
so,
spatial.
so if we have more number of pages, then obviously we are more considering locality of reference. I mean, I am thinking that perspective. But in FIFO, I mean, if we have only less number, like 4 or 5 pages in the frame, I mean, a stage table, then obviously FIFO will be better. Maybe, I mean,
Yeah, but if the frame count is also less, right? Um,
yeah.
then anyway, LRU won't work, and it would degenerate into FIFO anyways, right? How would you find the victim page then? You should transform it into a FIFO only. Say like everything is accessed only once. Which one will you evict out? everything is recently
Yeah,
used
yeah,
only. So
yeah. So suppose is there a question like in what scenario FIFO is better than LRU? So we can say that where we have less number of pages, then FIFO might be better than LRU.
yeah, it might be better. It might be equal, not better.
Okay.
It might be equal,
Okay. Thank
right? So this LRU actually, I guess I had explained LFU. Mm, uh, least recently used as in least frequently used. I had explained actually because I was taking the number of times it is referenced, which is the frequency information, right? Sorry, this least frequently used. LRU is different from frequently used as in which
you.
one?
The last
Yeah,
page. Yes.
the last thing which was used, so it considers that. Whereas, right. So in that, so actually I explained LFU. Okay, so sorry for that confusion. But anyway, LFU or LRU, taking either of these information, right? The frequency or the recency, it is better than just following the FIFO model. So that's what Validy's anomaly is all about. Just blindly increasing the page frame count is as number of frames does not help. But as Nandan had mentioned, I'll try searching for any mathematical proof is also there and share that link in the slides. So in that case, let's move to question 5. Nandan, is that okay? Okay. So question 5, among the following algorithms, which one has the least rate of page fault?
Optimal.
Okay. So the correct answer is option B, optimal, because it looks into the future reference string also, but it's impossible actually to look at the future references. But this one is, theoretically speaking, this one has the least page fault rate. So question 6, which of the following algorithms does not suffer from Validity anomaly? FIFO, optimal, LRU, or option D, both optimal and LRU? Right. Option D is the correct answer, as I had explained before. FIFO suffers from Validity anomaly, whereas optimal and LRU doesn't suffer from this anomaly. So if no doubts in this question, then let's move to question 7. Which of the following counting algorithms are expensive to use and considers the argument that the page with the smallest count was just brought in and are said to be used? So you is it LFU, MFU, or both A and B, or none of the above? Any guesses? Right. Option B is the correct answer. The thing is, both LFU and MFU both are counting algorithms only. It uses the count information. So, in that example which I mentioned, like not LRU, like the LFU example which I explained in while explaining Validity anomaly. So, both LFU as well as MFU utilize the frequency information, but since they are using this actual count, right, it say like a page can be referenced n number of times. So what is the maximum n value that you should be storing? Is it like 64-bit value or is it 32-bit value? So because, and for each page you should be maintaining that count value. So counting algorithms in general are very expensive to use, because apart from your page that you are storing, this metadata for storing that count and all those things you should be maintaining, and incrementing the count on each reference or decrementing and all those things. So that extra overheads is very expensive. But out of LFU and MFU, MFU is the one which follows the argument that the page which was with the smallest count is just brought in and is yet to be fully utilized by your process. So it's just brought in, it's a new page and it's yet to be utilized, and the assumption is that in the future that newly brought in page will definitely be referenced multiple times. So keeping it in your uh, in the frame would be beneficial. So MFU will remove that most frequently used page, assuming that since it's used many number of times, I'm assuming that in the future it won't be used those much number of times. So I would be safely removing that page from that frame. So that's what MFU is all about. LFU is the opposite of MFU. Okay, so both LFU and MFU are counting, but based on this argument, only MFU is the correct answer. Option B is the correct answer. Any doubts in this question? Question 7. Right. If no doubts, then let's move to question 8. Which of the following statements are true? The process execution time can vary a lot in local replacement and global replacement, or the memory utilization is better in local replacement as compared to global replacement, or is it the process selects a replacement frame from a set of all frames in global replacement, while each process selects from only its own set of frames in local replacement, or option D, all of the above. Any guesses? Option D. Okay, Nandan's mentioned option D. Let's say one by one. A process execution time can vary a lot in local replacement than global replacement. So what is local and global replacement first of all? Say P1 is allocated some 3 frames, F1, F2, F3, and P2 is allocated some 4 frames, F4, F5, F6, F7. Now say P1 wants to access some new frame, okay, so, some new page, okay, say this is 3 pages are present already, okay, and now P1 wants to access P4, and based on the reference information, I have noticed that P2 in process 1, so um, this is process, okay. So this is process 1, process 2, and this P1, P2 are actually page 1, page 2 and those things, okay. Sorry, I used the same P notation, okay. So this process 1 is now wants to access page 4, and based on the information, the OS has, based on the reference string for process 1 and 2, it has found out within process 1, page 2 is used less till now, and page 3 is used less in process 2. Now which one should I swap out? So in a local replacement, what happens is I should swap out page 2 only and bring in page 4 in place of page 2. In global replacement, what I can do is if page 3 belonging to process 2 is referenced only once, whereas page 2 in process 1 is referenced 10 times, then it is better if I allocate this frame 6 to page 4 belonging to process 1. So that is global replacement. So removing a page belonging to another process from that frame and bringing in another process's page into that frame. So that is global replacement. You view the whole set of frames as a single entity and just do your replacement policy. In local replacement, you should just replace the pages belonging to your process only. You should not go and touch the other process pages. That is local and global replacement. Now the fact is your memory utilization would be better when you take into consideration your global replacement only and not
I
local
have
replacement.
I have a question for that. I mean,
Okay.
how is it possible that we can access another process page, or a process? I mean, Is
So
it not
this virtual memory
security?
is taken by care of your OS, right? The OS will have it won't be accessing your page as in. It will be accessing the page table only. So the mapping should be changed, right?
Okay, so is it possible that we can access different process, I mean,
No,
simultaneously?
no. So the
I mean,
thing is
what
the
am actually getting confused, like the security issues when we have, memory access of
yeah, yes.
different processes.
Yeah, so the thing is your process 1 is not allowed to directly access process two's pages. If process 1 tries to access something in page 4, right, it will result in a page fault, and your the handler would be running in the kernel mode.
But here OS is accessing, that's why it's possible, right?
OS is,
Accessing the pages, that's why it's possible. I mean, it's not possible for a process to access another process page,
yeah,
but it's possible for OS.
of course the OS should have full control over all the processes, right?
Okay,
That's
got it.
the medium of interaction, cooperation, everything. So of course it should have access. So that's what the OS is all about, the memory management and those things.
Okay, thanks.
Yeah. So two things to note is one is memory utilization, and the other is process execution. So your memory utilization is better in global replacement, not in local replacement, because say if it's just local, right, only these 3 frames is allocated to this process, and assuming that say p1, p2, p3, all these 3 pages are frequently used, but it has to get in P4 and use that also actively. So it has to evict some frequently used page out of these 3 P1, P2 and P3 and get in P4 and swap in and swap out, and it will result in increase in page fault only. If we say like P2 is more frequently used in the future also, right? So the number of page faults will increase. But if we say that page 3 in process 2 is just used only once, say some initialization function is there or something, only at the beginning it is used and it is never touched throughout the rest of the process's execution. So we can safely allocate this frame to process 1's page 4. So you can efficiently utilize the whole set of frames and take into consideration the global view of your page references by each process and allocate those many frames optimally. Say in the first set of first 10 minutes, one process will be actively using your memory. In the next 10 minutes, another process would be actively using the memory. So in a global replacement policy, since you are taking the whole set of the frames into consideration and not localizing it, your whole memory utilization will be better, because in the first 10 minutes whatever process is utilizing your memory uh, more, that would be given preference and it would be utilizing more memory in a global replacement policy. In a local policy, it will just be confined to those set of frames only which it is being allocated at the first, and it should just recycle those frames only, reuse those frames. So the overall utilization, if you notice, it will be better in the global replacement, because you take the frequency information, all those things on a global view and not just limiting to a process. So your memory utilization is better in global replacement. So option B is false actually. It's given the opposite. Now coming to process execution, the process execution time, say if I'm running process 1 now, it's taking 5 seconds. After some time, if I rerun that process 1 again, it should take the same mostly that 5 seconds or something. But say if you are running like 10 processes together, like process 1 till process 10, you are running all these 10 processes together, and process 1 takes 5 seconds to complete in this scenario, say now, and later after 1 hour or so again you run these 10 processes, and now also it should take the same 5 seconds or something around that time. So that is like you are having like a deterministic process execution time. This will be the case in local replacement policy, because say assume like you're keying in the same options in process 1. Say it's asking for some input or something, and you're keying in the same options for process 1, and in that case your process execution time in your local replacement will be the same, because that process 1 would have been allocated say 5 frames. So within that 5 frames it would be reusing all those 5 frames, swapping in, swapping out all its pages whatever it's using, and if the same input is given, it will be going through that same control flow, that if condition, those things. It will be accessing the same data, all those things. So that same set of page reference strings would be accessed by process 1. So that same page fault rate would be maintained by process 1, and that would result in approximately the same process execution time overall, 5 seconds. But now if you consider the case of global replacement policy, what happens is we cannot assume that the same input is given to the remaining 9 processes always. So what happens is, say now if I'm executing these 10 processes, process 1 takes 5 seconds, and the remaining 9 processes, I would have given some input, the user would have given some input. Based on that input, a set of pages which are accessed by process 2 and process the remaining 9 processes would be say some reference string is produced in some set of pages are referenced. Now after 1 hour, the same 10 processes you are executing. For process 1 I am giving the same input, but for the remaining 10 processes, if I am giving different inputs, in a global replacement policy, the replacement policy is taken in global scope. So based on how the other 9 processes are utilizing your memory, the replacement policy will sometimes swap out process one's pages also out of memory and get in other processes pages. So you get the notion, right? It's not deterministic, the execution time. In a local replacement, it's deterministic, because the set of frames that it's allocated to a process is always the same. You, it's local, so you based on that reference string, I can very well say it will take 5 seconds or something, the set of pages it wants to access. Whereas in a global replacement, I should take into consideration what the other processes might be accessing, how frequently they will be accessing their set of pages. So based on all those things only, I would be able to tell whether my process would be experiencing some increase in page fault or decrease in the number of page faults based on the other processes memory utilization. So the process execution time can vary a lot, not in local replacement but in global replacement. So option A is wrong. So option C is the only correct answer. The other options are wrong. So option C just explains what global replacement is and what local replacement is. So any doubts in this question, why A, B are wrong and C is the correct option? Why the execution time varies in global and the memory utilization is better in global? Any doubts in this question? Right. Okay. Thanks, Kan. So in that case, let's move to question 9. Which of the following statements is true about trashing? It makes the OS to think that it needs to increase the degree of multi-programming. It needs to lower the CPU utilization. It leads to low CPU utilization. A process is added to the system, or all of the above. Right. So as Nandan has mentioned, option D is the correct answer. Trashing is nothing but say your working set, whatever you are using, actively being used, those all that pages you cannot be able to fit into your frame count, those things, right? So in that case what happens is it it will lead to a more number of page faults. Once it leads to more number of page faults, so page fault is nothing but you are waiting for the disk operation to bring in your page from the disk into your main memory. So once it request goes to the disk IO, your process would be moved from the ready queue to the waiting state. So if that say all your processes or something like that, if those processes are each waiting uh, waiting for the waiting for some memory which has to be swapped into your main memory from the disk, right? So all the processes might be going into your waiting state, and none of the processes will be present in your ready queue for execution. So in that case, what happens is, since your the OS scheduler sees that none of the processes are there in ready queue but still in waiting state, what the scheduler will think is it needs to bring in more processes to increase the CPU utilization. So what it will do is it will bring in more processes into the ready queue. And now again what happens is, already some pages, since the memory utilization is very high, getting in more pages, those getting in more processes, those processes will result in more um, the increase in triggering these replacement policies, because those processes will also have some set of pages it needs to access, so it will try to bring in those set of pages again. So again from ready queue, those processes will also go into the waiting queue. So in a way, like trashing is like, the scheduler thinks that okay, everything is in the waiting state, I have to I can bring in more processes to increase my utilization, but it doesn't register that it doesn't think that the active memory space is small and all the processes are contending for the same memory space. That's the reason of why this low CPU utilization is present in the first place. So without thinking of that, blindly just bringing in all the processes will still further degrade your CPU utilization only, and it will just result in a long list of processes present in your waiting queue, waiting for the pages to be brought into memory. So that is what crashing is all about. So option D is the correct answer. Any doubts in this question? Right. If not, then we'll move to question 10. Which of the following does not help in limiting the effects of trashing? Is it a local page replacement policy, or global page replacement policy, or priority page replacement, or none of the above? Any guesses? Okay. So the answer is global page replacement, because in a local page it is not affected by how the other processes are using the memory, or utilize number of pages it requires, the active set of pages it requires, those things. Whatever frames it has been allocated, within that only it can replace and play around with and bring in the extra pages and all those things. So local page replacement actually reduces it doesn't get affected by this trashing scenario actually. Priority page replacement will actually uh, give more priority to, it's like a global page replacement, but it will give more priority while swapping out pages to the um, based on the priority assigned by that scheduler. Based on that, the pages selected among all the processes as the victim page would be chosen based on this priority information. So in a way also, it, since some priority is being used, right? So based on that, at least one process would be the highest priority process, would be making some progress, and once that process has finished execution, all the frames allocated to that process will be freed, and the other processes might use that freed memory space in a priority page replacement. In a global page replacement only, what happens is it it actually does not help in limiting the effects of crashing, because why does crashing occur in the first place? When the when the thing is, one process's memory utilization affects some other process's page fault rate, and it goes like a domino effect, and finally all the processes face an increase in the number of page faults, and all these processes, like a domino effect, they just go and sit in the waiting queue, and the scheduler mistakes it and brings in new processes into ready queue. But for these new processes also, you have to bring in the pages and all those things. So it's like a domino effect, and the global page replacement is an ideal candidate for this crashing phenomenon to occur. Whereas in local page replacement or priority page replacement, crashing will not occur, because crashing would be limited in priority page replacement. In local page, crashing will not occur at all, because your set of pages is fixed for that process. It can just swap in or swap out within its process only. So whatever that process, how much ever it's utilizing its memory, it won't affect the other processes. So local page replacement does not have the crashing effect, whereas in priority page replacement, it's built on top of this global page replacement, so that at least one process gets more priority and finishes execution, so that it frees up some memory space for the other processes to continue execution. So option B is the correct answer, as in just using global page replacement policy would not limit the effects of crashing. Any doubts in this question? Right. If not, then we'll move to question 11. Consider allocation of memory to a new process. So assume that none of the existing holes in the memory will be exactly fit the process's memory requirement. So hence a new hole of smaller size will be created if the allocation is made in any of the existing holes. Excuse me. So which one of the following statements are true? Is it option A, B, C, or D? So they have given a scenario, like say this is your memory, and none of the existing holes will exactly fit. So say this part is allocated and this part is allocated, and say this is 100 bytes, and this is 120, and this is 50 bytes, and you're requesting allocation for say 40 bytes. Okay. So this is the assumption, like assume that none of the existing holes will exactly fit the requirement. So this 40 bytes, there is no 40 bytes hole as such. If you want to place 40 bytes in any of the free regions, it will lead to a split up of the holes actually, because a new hole of smaller size will be created if the allocation is made in any of the existing holes. So if it's made over here, then the remaining 60 bytes would be a hole. If it's made over here, remaining 80 bytes, and if it's made in this hole, then 10 bytes remaining would be a hole. So in any of the three holes, hole 1, hole 2, or hole 3, uh, we cannot fully properly exactly fit. There will be a new hole being formed, which is of a smaller size. Now the question is, which one of the following statements are true? If I follow a worst fit strategy, the new hole that is created will be larger than the hole created by the first fit policy. Or is it the case that if I create a hole using the best fit strategy, it will be never larger than the hole created by the first fit strategy? Or is it option C, hole created by first fit is always larger than the hole created by the next fit? Or option D, the hole created by next fit is never larger than the hole created by best fit? So if 40 bytes is allocated to any of the holes, that remaining hole, that newly created hole, right? That is what they are mentioned by hole created, right? So Nandan has mentioned option B. So option B is the correct answer. So let's just briefly see what every option is all about. So worst fit, what does worst fit talk about? Worst fit is find the largest hole and just split it. So the hole created would definitely be um, say it will be getting to 120 bytes. So the remaining hole size would be 80. That's the new hole that is created. And in a first fit, um, it's the first hole that is present in your memory. If you start scanning from the address 0, so so hole 1 it will try to allocate. So this one will allocate in worst fit, and this one it will try to allocate in first fit. So this one is the remaining hole size is 60 bytes. So the hole created by worst fit is always larger than the hole created by first fit. Not the case, right? Assume that my first free hole that is present is of size 120 bytes, and this is 100 bytes. Now what happens? Your worst fit will also select this hole only. Your first fit will also start scanning from the first address for the first free hole, and it will allocate that free hole, seeing that 40 bytes can be fitted into 120 bytes. Okay, so this statement, the hole created by worst fit will always be larger than the one created by first fit, is wrong, because we have a contradicting example where the first hole can be the worst hole also, which can be allocated. So in that case, it won't be larger, it will be equal. So option A is wrong. Now coming to option C, what they are telling is the hole created by first fit will always larger than the hole created by next fit. Okay, so so consider that say you are having 120 bytes over here. So this is also 120 bytes. So hole 1 is also 120 bytes. Hole 2 is also 120 bytes. In a first fit, what happens? It will start scanning from first, and it will see, okay, hole 1 is 120, 40 bytes can be stored over here. So it will allocate hole 1, it will create a hole of say 80 bytes. And now in a next fit, what happens is, say the scan pointer is pointing over here. This one is the last allocated hole. So that scan pointer will start scanning from this location. So if it starts scanning from this location, it will see, okay, the starting itself it sees 120 bytes, 40 bytes can fit in over here. So the remaining 80 bytes hole it will be forming. So if you see in a first fit or a next fit, the same 80 bytes is being created, hole size. So the statement that hole created by first fit is always larger than the hole created by next fit is false, because we found a contradicting example. In the same way, if we see, take the option D, hole created by next fit is never larger than the hole created by the best fit. So they are telling, like, whatever the hole created by the next fit algorithm will be never larger than the hole created by best fit. This is just seeing at this option, it's wrong, because say if starting from this scanning point, right? If your next fit algorithm starts, it will see 120 bytes, it will allocate and it will create a hole of 80 bytes. But in a best fit, it will see which one has the best, the least hole size pertaining to this 40 bytes. So 50 bytes is the least one it can find. So the 10 bytes hole would be the newly created one. So NextFit has created 80 bytes, whereas BestFit is created 10 bytes. But it's telling NextFit will be never larger than the hole created by BestFit. So we found a contradicting example for option D also. So coming to option B, then it's a final option. They are telling the hole created by BestFit is never larger than the one created by FirstFit. So you cannot contradict this example because best fit will always result in the smallest hole. The smallest hole size created, that is what the best fit algorithm is all about. And they are telling that whatever hole size the best fit algorithm creates, it will never be larger than the hole created by first fit, which is always true because the first hole which is going to be allocated can be the best fit, but any other thing smaller than the best fit, whatever hole that is created by the best fit or selected by the best fit cannot be found, because best fit is, the meaning itself is it's finding the smallest hole, that's the best fit, right? So that's what the algorithm is all about. So option B is the correct answer, as Nandan has mentioned. So any doubts in this?
Can't we have a situation scenario where first phase is also very small, like,
No,
and,
so no,
and
you
rest it depends upon the kind of process. I mean, which is
no, it don't depend, right? See, what does first fit is all about? Start scanning from the first location in the from the zeroth address. It starts scanning, and whatever it finds, which finds it is which can occupy that 40 bytes, it will allocate that. And say if it finds 39, it cannot allocate the least size it can find. It should find is it should find 40 bytes itself. Say one 40 byte hole is present. When will first fit find it? When it's present at the starting itself. Whereas best fit, it will find it always. Right? You get the point, right? So the best performance in first fit will always be the answer written by this best fit algorithm only.
yeah, got it.
Right? Okay. So if in that case, if there are no doubts, then that brings us to the end of the session. Uh, thank you so much for making the session interactive. Uh,
Yeah, and
uh,
if you
and yeah,
stop the recording.
1 second, Shashikant. Yeah, and Nandan, as you had mentioned, I will add a link to any paper which mathematically explains more about this Validity anomaly into the slide. Right. And if you want, you can just ping your email ID or something. I can mail you also the link if you, right, if you are okay with that. Okay. Right. So in that case, thank you everyone. Thanks for attending the session.